In this video we'll be going over how to make a peristaltic pump. Peristaltic pumps are useful for pumping known quantities of liquid without risking the liquid damaging anything it shouldn't. I need some peristaltic pumps for an upcoming project, and although they can be purchased, the ones I found are either too expensive or not fit for purpose. Therefore, I've made my own. And in this video we'll show you how to make your own, as well as calibrated it, showing mistakes along the way so it works for your first time every time. And here is the wiring diagram. For this I'm using a AZ delivery or AZ delivery D1 board ESP8266. I've got an A4988 stepper motor driver, a 100 microfarad capacitor, the NEMA 17 stepper motor, and a power source. The enable pin of the A4988 is put to pin 12 on the ESP8266. The step pin is put to pin 13 on the ESP8266, and the direction pin is put to pin 15 on the ESP8266, but of course you can change this if you wish. For smoother operation, we're using all the micro stepping we can get, and therefore MS1, 2 and 3 are tied to the power rail as well, which comes from the 3.3 volts of the ESP8266. Meanwhile, the ground is common ground, and the 100 microfarad capacitor is put across the VMOT and the ground of the A4988 in order to smooth out the power provided to the step motor, just so that it runs more reliably and consistently. We then have a 12 volt power source which runs the VMOT, which is then going to be the power to the step motor, and ground is common ground as well. Make sure that the ground from the power supply is also connected to the ground from the ESP8266 or Arduino equivalent, whatever you're using. And then wiring up the NEMA 17 to the A4988 is simply done here, making sure the coils are matched appropriately, and do double check the pinout of the A498 as yours may differ, but by and large they're all the same. And here is the code for the peristaltic pump. So to begin, we need to label the step pin as 13, direction pin is 15, and the enable pin is 12, and then steps per revolution, because it's full micro stopping, is 3200, and step delay that I found is 60, and this is going to be in microseconds, as we'll see later on. I then have a few different integers which are useful for accelerating and decelerating the stepper motor, which isn't necessary, but I use for smoother operation to limit back EMF, and it enables it to get to higher speeds. The M value of 600 here is used for accelerating the stepper motor, and the milliliter amount in steps is for the serial monitor for your own use, and is also important for calibrating. And then steps per milliliter, as I have calibrated it, turns out to be 3921, but we'll get to that momentarily. To begin, the step pin needs to be an output, direction pin needs to be an output, and the enable pin needs to be an output. I start the serial monitor as well, have a short delay, and then write the enable pin as high, and this disables the stepper motor driver, so there isn't power running to the motor doesn't overheat, the motor driver doesn't overheat, and it doesn't waste power either. Next we have the function for accelerating the stepper. So what I've done is, obviously I know that M is 600, all the time that that's more than the step delay, which is 60, it's going to minus, and it's going to do each twice, because that's T. And what it's going to do is put the step in as high, and then put the step in as low, delaying with whatever the value is, anywhere from 600 down to 61. And the yield function is vitally important for a long function like this, for the ESP8266, otherwise it will just conk out. And then same for decelerate stepper, but same but opposite. So it starts at step delay, and then it goes up to just under M, so 599, and adds, and it does each twice as well, so that it slowly decelerates, and again we've got the yield to make sure that it behaves itself. The accelerate stepper backwards and decelerate stepper backwards is good if you want the motor to run both ways, so if you want to pump from vessel A to vessel B and then from vessel B to vessel A, which I haven't bothered doing, but you can, it's there to use. And then for the spin stepper and spin stepper backwards, so to start we want to accelerate the stepper, wonderful, or the stepper motor rather, and then we want to move it for a set amount, which I'm using placeholders of I and R for the time being. So I will stay at 0 and increase up to R, and R will be the milliliters that you use, which I'll show later on. So again, step in high, delay, low, and yield to make sure that it behaves itself. And then make sure that I is back to 0 again at the end, and decelerate the stepper so it stops. Wonderful. Same thing for stepping backwards, but in reverse. So now the main loop, this bit up here, if serial.available is more than 0, which is to say you use the serial monitor, and if you put a number in, then if it's more than 0, what will it do? Well, it'll pass it as an integer, so it is an integer. It'll then tell you what it is, and if it is more than 0, then the milliliter amount in steps will be the integer you've entered multiplied by steps per milliliter, which we've already calculated 3,921, minus the placeholder for the acceleration and deceleration times 2. So it accelerates and it decelerates before it ends as times 4. It will tell you the amount in steps, and then once it's told you the amount, it'll actually behave. First off, it will weigh the in pin as low, so that the stepper motor driver wakes up and moves. It'll tell you that it's spinning the stepper, and it will spin the stepper using the value of R. So if we plug that back up to the spin stepper, you'll see now I is R. So if you say 10 milliliters, then that is what it'll do. And then to finish, we want to put the enable pin as high again so that it disables the stepper motor, and then R is equal to 0 so that it doesn't repeat. For calibration, the first thing you need to do is fill up the peristaltic pump so that it has water all the way along it. Then put the dispersing end into a measuring jug or into a vessel on a scale. Water is near enough 1 gram per milliliter, so it'll be fine. Then, into the serial monitor, enter a known integer, such as 10, I'd recommend, and record the total output of water. Obviously, the bigger number you use, the better the result will be. Now that we know that the steps per milliliter as standard is 3,921, and you said 10 milliliters, that's going to come out as 39,210 steps. And then you record the amount that comes out. And let's say, for example, you have 12.3 milliliters coming out. That means that you know 39,210 steps equals 12.3 milliliters. So with those figures, now all you need to do, going back to the one above, is take the total steps, which in this case is 39,210, you divide it by the 12.3 milliliters, or whatever number that you have that came out, and for 12.3 we find that that equals near enough 3,188 steps. So with that known quantity, we now go back over to the steps per milliliter and we change that to 3,188. Just like that, it's calibrated. By all means test it again to make sure, but that's done.